Hello, today we're on to lesson 3 of capacitance. So over the last couple of lessons we've covered up to point E on the specification. Today we're going to look at the electric field generated by the capacitor and also look at the equations for the energy stored by the capacitor. Firstly, looking at the electric field, this is what the electric field would look like. The top two diagrams are a more realistic version of it, where on the outside we have this bending effect known as fringing or an edge effect. That's a more realistic picture of it, but we don't actually take that into account for the A-level course. So the lower version is what we would need to replicate in an exam if we were asked to draw the electric field. We just draw perpendicular lines to the plates, equally spaced all the way across, and the field flowing from the positive plate to the negative plate. So we end up with this uniform field between the plates and don't actually show that fringing on the edge. There's also an equation for this. Now you don't need to know the derivation, but just for you to be aware, and for our mathematicians in particular, it comes from the idea that the charge would be related to the material that we have in between. So at the moment we're dealing with the vacuum or air, so we have the relative permittivity of free space, and then it's the integral of a closed space. And we integrate the electric field in relation to the area of that surface. This gives us Q epsilon O electric field A. And we simply manipulate this. Now we know from equation 1 that Q is equal to VC. If we then divide through by D on both sides, and equation 2 shows us that C is equal to epsilon O A over D. So we can actually get rid of those four terms. And we're left with V over D is equal to the electric field, or our third equation. Electric field is the voltage, the potential difference, divided by the separation. Moving on to G, looking at the energy stored within a capacitor. So we're going to look at this from a typical example of a capacitor being charged, fully charged or charged up to a particular point, and then the energy that gets released as we discharge it. So if we put the energy in and then release it a little bit at a time, the charge and the voltage gradually drop. And we end up with a graph like we see in the bottom right hand corner. So we get this straight line. So we are imagining that we are discharging it a tiny amount and then taking more measurements and then discharging it again a tiny amount and making more measurement, and you get this stepped effect. However, if we make that discharge infinitely small, the width of those strips become very, very narrow, and we end up with a perfectly straight line. So the charge and the voltage are directly proportional. Now, the total energy stored will be equal to the area underneath that graph. So it's obviously a triangle, so it'll be half base height, or half times Q times voltage. And this gives us equation 4. Now this is in our data booklet, so the energy stored is the area under that graph, as I say. So U is the energy stored, the electrical potential energy. Q is the charge, which comes on the y-axis, and V is the potential difference from the x-axis. Now you need to be able to manipulate this equation as well to generate others. Alternatively, you would be able to take it as an approach of you would find out other pieces of information using other equations and then use the original form. So it doesn't really matter which approach you go for, but it's obviously easier if you can do the substitution and then one calculation. So firstly, we can substitute in equation 1, which is in the data booklet. Q equals VC. Okay, so we substitute the VC in for Q, and we end up with V squared times C, or CV squared. And again, for the next one, we can rearrange equation 1. So rather than Q equals VC, we say that V equals Q over C, and then we substitute that in for V instead. And we end up with half Q squared over C. So you should be able to rearrange and use any of those formats when answering questions. We put together a lengthier task for today. It's looking at consolidating the earlier equations as well. So you'll need to use equation 1 and 2, as well as what we've looked at today. And it's looking to extend those questions into something that's closer to examination style. So 6 questions there. As I say, they are lengthier, so it'll take a bit more time than the previous tasks. But have a go at those and let me know if you've got any